this time without interruptions. Yay. Okay, so we talked about functions. We already know that a relation from A to B is a subset of A cross B. Well, f is a function, means it is a relation from A to B, so it is also a subset of A cross B. But for it to be a function from A to B, I need the domain of f to be all of A, and if x, y, and xz are in f, then y equals z. This is the same thing as the vertical line test. So we can write f colon A arrow B. This means it is a function or a mapping. Those two words are interchangeable. If A, so A is the domain, B is the codomain. The range is anything in B that got hit by something from A. Okay. That is not a new definition. Okay, so let's say, and if A equals B, we say f is a function on A. I should have read this in advance. This is annoying. Okay, so let's look at an example. Suppose A is a set 1, 2, 3, and B is a set x, y, z. If I look at f being the set of 1, x, 2, y, 3, z, this is a function. Another example. Oh, and I can use this notation. This is a nice notation. Sometimes it's more visual. I can see that there's each thing over here in A has only one arrow coming out of it, not two. That tells us it's the vertical line, passes the vertical line test. And everybody in A over here has something coming out of it. That means the domain is A. Let's look at this one. F is 1x, 2x, 3x. So this is also a function. But if you look at f inverse, x1, x2, x3, this is not a function. Just showing that sometimes the inverse may or may not be a function depending on what your original function is. Yeah, that's as far as I wrote in advance. Now, let's see. Let's talk about some of these. Let's talk about a projection map. That was something else we had. Okay, projection map is just saying you're going to take something that has a bunch of ordered pairs and you're going to map it to a particular coordinate. Okay, so let's say I have S is a subset of R cross R. This is going to be different from class. I'm going to let S equal the set of x, y such that x squared over 4 plus y squared over 9 equals 1. Okay, give me a second. I lost my... Okay, good. Use that. So this is the parabola, not the parabola, the ellipse. Okay, 4. I go side to side by 2 and up and down to 3. Okay, believe me, that's supposed to be an ellipse, even though it doesn't look like it. I don't have any points that I know that are on that particularly, but I want to tell you that the range of pi 2 is, okay, pi 2 takes you to all the y coordinates. So this is going to be the y's that got hit. So you're projecting or squooshing this ellipse down to any possible y that got hit. So this is anything from -3 to 3. And similarly, the range of pi 1 are the x's. So that's going to be from -2 to 2. The circle was unfortunate because the range of both were the same. Okay, so we can look at another example. Let's say I have S is the set of x, y in R cross R such that y is equal to x squared. So a point in here might be 3 comma 9 is an element of S. So if I wanted to know what pi 1 of 3, 9 is, that's the x coordinate. Pi 2 of 3, 9 is the second coordinate, 9. Let's look at this other function, this chi of a of x, which will equal 0 if your x is not in A, and 1 if x is in A. So an example of this, and this depends on my universe. Let's say my universe is the real line, and A is the set from open interval 0 to 3, closed interval. I don't really care about the whole thing. So from 0 to 3, here's 0, 1, 2, 3, close dot, open dot, all this is 1. And everything else in my universe is 0. So that's that funky function. Our theorems. I already typed up the proofs and I sent them to you, so I'm going to expect you to look over them and understand them. But let me just rewrite what the theorems are. Two functions f and g, are equal if and only if the domain of f equals the domain of g, and for all x in the domain of one of them, doesn't matter since they're equal, f of x equals g of x. So why does this make a difference? Well, if I have f equals the set of xy, element of r cross r, such that, how do I want to do this? Y equals x squared. I want to say x squared. I'm going to say x to the 4th. Okay, so the domain of this function is the reals, and the range is just the positives. And the range, well, including 0. If I have g equal the set of xy in the complex plane, but the same notation, y equals x to the 4th, well, now I have a possibility of having I comma 1 in my set. But I comma 1 is not in f. So here f does not equal g. Not the best example, but that's a start. Okay, next theorem. The composition of functions is a function. That was the point of this theorem. If f is a function from a to b, and g is a function from b to c, then the composition, g composed with f, is a function from a to c. We already know that if f is a relation on a cross b and g is a relation on b cross c, then the composition is a relation on a cross c. But I wanted to talk about it being a function. So we now know the composition of functions is a function. Definition. Sometimes we're going to want to restrict our domain. So suppose f is a function from a to b, and d is a subset of a. Well, if I say f is a restrict it to d, this means the set of xy in f such that x is in D. So it's the same function, it's just some subset of that function. This is also a function. F restricted to D is a function from D to B because we restricted the domain. The last theorem that I didn't get to, because y'all are driving me crazy, is suppose I have f is a function on A. I don't know where it goes. Let's say, doesn't matter. I don't want to restrict it. Let f is a function such that the domain of f is A, and g is a function such that the domain of g equals B, and A intersection B is empty. So their domains have nothing in common. So we want to kind of glue these two things together, and we do that by the union. So I can say that F union G is now a function from A union B to wherever they went to. So the key is F union G is a function. We can glue functions together if we know that their domains do not intersect. We could also glue them together if we know that they agree on the domain. If wherever their domains agree, they have f of x equals g of x. So that will also be a function. Now this proof is also in your notes that I sent you, and I expect you to look at that. Now let's think what homework I gave you that you might not have. Okay, so let's say I tell you that A is equal to 5, 6, 7, and B is equal to 3, 4, 5. And R is a relation from A to B. I want to find an example, find an R such that R is a function from A to B where such that the range of R does not equal B. And that just means I'm not hitting everybody in B. Doesn't mean I can go out of B. R must be a subset of A cross B. So I still need things from A, things from B. So if I have a function from A to B, that means I have to have 5 goes somewhere, 6 goes somewhere, and 7 goes somewhere. I don't want the range to be all of B, so I can't use 3, 4, and 5. So I could just say 3, 3, 3. That's an example. I could have said 4, 4, 4. I could have said 5, 5, 5. I mean, there are lots of different examples as long as we don't use all 3 of them. Ooh, that might be an interesting question. How many of such functions are there? Maybe we'll talk about that in class. Cool. So that's kind of a recap, quick recap of the lecture to go along with the notes, the proof page that I sent you last night. So hopefully this will help.